Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So basically in this video we are going to continue our discussion for chapter 1, which is magnetic circuits. Okay, and then in this video we are going to cover the last 3 subtopics, which is the first one is the fringing effect. We will go to see what is the fringing effect and then what caused the fringing effect to be happen. Okay, and then after that we are going to see the different category of magnetic materials, include the ferromagnetic materials. So what does the ferromagnetic materials differ from others? And then finally we are going to see the type of losses in the ferromagnetic core. Okay, so basically two different losses that we are going to learn. The first one is the eddy current losses, and then the second one is the hysteresis losses. Okay, alright, so let's move to the first subtopics of today, which is the fringing effect. So what is the fringing effect, and then what are the phenomena that cause the fringing effect to be happen? So first of all, before we learn about the fringing effect, we must learn about the concept of magnetic circuit with air gap. Okay, so you can just consider the first picture represent the magnetic core without the air gap. Okay, so you can see it is a uniform core material. Okay, so this one can be represented by the magnetic equivalent circuit, which is you have a magnetomotive force here, and then you have a only single reluctance here. So this is considered as your reluctance of the core. Okay, so consider that you have a magnetic core with the air gap. Okay, so here you have a you have a core with the reluctance of RC, and then here you have an air gap. So air gap have a reluctance of the air gap. Okay, so in the electric machine, the rotor is isolated from the stator by the air gap to reduce the saturation effect at the core or at the poles. So that's why usually in the electric machine, you will be using the magnetic circuit with the air gap. Okay, so you don't have this in your electric machine, but you have this. Okay, so the magnetic circuit having 2 or more medium, usually it will consist of magnetic core and air gap, or maybe magnetic core with the 2 air gap. It depends. It's known as the composite structure. So this is what we call as a composite structure. So usually we employ the composite structure in the design of the electric machines. Okay, so when you have a air gap in your magnetic circuit, so what will happen? The fringing effect will be happen. Okay, so at the air gap, as you might see here, let's say you consider one case that you don't have the air gap. So you can see the magnetic flux flow directly from this core to this core. Okay, so let's say you have a very small air gap there. So it will cause the fringing effect. So this is what we call as a fringing effect. Okay, fringing effect, or in the other word, at the air gap, the magnetic flux flowing in the magnetic core spreads out into the surrounding medium, meaning that it is fringing out from to the surrounding medium. Okay, so this is what we call as a fringing effect, or this is this line is considered as a fringing flux. For let's say the air gap it become more larger, so the more fringing flux or the more fringing effect can be happen. Okay, this is what we call as a fringing of the flux or fringing effects. So fringing is actually directly proportional to the length of the air gap, meaning that the more length, so if the length increase, the fringing effect also will be increased. Okay, so the less air gap, the less fringing effect will be happen. The leakage flux is defined as the magnetic flux which does not follow the intended path in the magnetic circuit. So this is what we call as a leakage flux, because it does not follow the intended path. This is the intended path of the magnetic circuit. Alright, so the one that become outliers here is considered as a leakage flux. So the useful flux is actually the flux that pass through the core and is utilized in the magnetic circuit. So this is what we call as a useful flux. So here is considered as a useful flux. Alright. Okay, so the longer the air gap, the greater is the fringing. as A is bigger in the air gap, so the magnetic flux in the air gap is slightly lower than the core. Okay, so here you see when the air gap is bigger, so it will cause the cross-sectional area for the air gap to become higher. So it will cause the magnetic flux at the air gap is slightly lower than the core. So the B of air gap is lower than the B at the core. Alright, so this is what we call as a fringing effect. So next we are going to see the second subtopics, which is the ferromagnetic materials. So all substances in the world are affected by the magnetic field. So basically there are three different groups. We can classify the substance into three according to the way they are affected by the magnetic field. Okay, the first one is the diamagnetic materials. So the diamagnetic materials usually show very weak magnetic effects. And then the value of the relative permeability mu r is very slightly less than 1. Usually the typical number is around 0.99999. Okay, so example of the diamagnetic material is such as gold, silver, zinc and copper and etc. lah. Alright. And then the second material is the paramagnetic materials. Okay, so for the paramagnetic material, is also show the very weak magnetic effects, same as per diamagnetic materials. And then the relative permeability mu r for the paramagnetic material is very slightly greater than 1. Usually, it's typically around 1.00001, something like that. Okay. And then example for the paramagnetic material is such as aluminium, oxygen, titanium, okay, etc. Okay. And then the last one is the ferromagnetic materials. Okay, for different from these two, for the ferromagnetic materials, it exhibits a very strong magnetic effects. Okay, and then it has a very large value of relative permeability mu r, usually typically around 10 to the multiply of 4. Okay, sometimes it can be 4,000, maybe 2,500. It depends on the material. Okay, later you will see in example the value of the relative permeability for the ferromagnetic materials. Okay, so the example for the ferromagnetic material is such as iron, nickel and cobalt. Alright, so that's all for the topics on ferromagnetic materials. And then the last subtopics, which is the losses in the ferromagnetic core, or we can also call it as a core loss. Alright, so basically there are two different losses in the ferromagnetic core. So the first one is the eddy current loss. Okay, so you can just consider this picture first. Right, so eddy current loss, we can also call it as a ECL. ECL takes place when a coil is wrapped around a core and AC supply is applied to it. Okay, so here you have a core. This is your magnetic core. And then you wrap around the core with the coil. So this is your coil. And then you supply the alternating AC current. Okay, alternating AC supply, you supply. So here you can see the direction of the AC going in, going out, going in and going out. So this may cause the magnetic flux to be alternating as well. Okay, so the magnetic flux will be going up, going down, going up and going down. Alright, so by Faraday's law of the electromagnetic induction, the change in the flux direction through the core will cause EMF induction inside the core. Okay, so because of this magnetic flux, alternating magnetic flux, it will cause the EMF induction inside the core. So the EMF, due to this EMF, the eddy current will start to flow in the core. Okay, so there will be eddy current here. So the blue line represent the eddy current, and the existing of the eddy current will be assumed as a loss in the form of heat energy. Okay, so this is what we call as a eddy current loss. Okay, alright. So eddy current loss can be reduced by lamination in the core. So you see here you have a solid core with no lamination, so you have a high eddy current. Okay, so in order to reduce the eddy current, so the engineer come up with the idea of doing the lamination in the core. So the core is sliced to every single slice here. So we will laminate it so that when we laminate it, so the lamination will produce low eddy current. So here, low eddy currents. Okay, so the thin sheet steel must be used which are insulated from each other. Usually, how we do the lamination, we are going to use the thin sheet steels. Okay, so due to the insulated sheets, the amount of the current which flow will be reduced, and hence the eddy current also will be reduced. Alright, so that's the theory on the eddy current. Okay, so next we are going to see what does it mean by the hysteresis loss. The second loss is the hysteresis loss. So for the hysteresis loss, it occurs when the amount of energy absorbed by the magnetic material does not return to its original path. Okay, meaning that the energy absorbed is not equal to the energy returned. So in order to understand this, we need to refer to the hysteresis curve. So this is what we call as a hysteresis curve. So basically the hysteresis curve is based on the magnetization curve, or we can call as a BH curve. So this is your B, this is your H. Okay, so consider you have any of magnetic material that the relationship of BH is given by this curve. Okay, so you have this curve. Alright, so consider you apply the current to your magnetic core. Okay, so you apply current. So in this case, you slowly apply your current. Okay, so what will happen when you increase the current? It will increase the magnetic field strength, which is your H. Okay, so increment in the H will cause increment in the B as well. Okay, so you increase your current, and then the H will be increased, B will be increased until it reaches saturation point. Alright, so this is what happens when you try to apply the current from 0 until saturated. Okay, and then after that, we try to reduce the current from saturation to 0 side. Okay, so what will happen now? When you reduce the current from saturation to 0, the flux density the flux density B will also start to decrease. Okay, so from this side it will start to decrease, but it will not follow this line, but it will follow this line. Try to decrease, okay, until you see that when your current is 0 now, it should be the flux density also 0, but it is not. So in this case, I is 0, but your flux is not equal to 0. Okay, so for 0 current, there is still some flux density present in the material. So this is known as a residual flux. Okay, because now when I is 0, flux is not equal to 0. So the remaining flux that live inside the magnetic material we call as a residual flux. Okay, alright. So this residual magnetic flux will get trapped in the core of the material and is lost in the form of heat. Okay, so this is what we call as the hysteresis loss. So the area of the BH curve will determine the amount of hysteresis loss. Okay, so it depends. For the material that has high permeability, so it has a small loop area. So in this case, it has a low hysteresis loss. Okay, but for the material that have a low permeability, so it has a large loop area like this. So it has a high hysteresis loss. Okay, so that's why the larger the area, the greater is the loss, and the lower the area, the smaller the area, the lower the hysteresis loss. Okay, so since the hysteresis loss depends on the material of the core, so it is important to use the material that have a high permeability. Okay, okay, so that's all for the topics on the core loss. Okay, so thank you for your time. Thank you for watching my video. I'll see you in my next video. Okay, bye.